Okay, we are looking at section 6.3, vectors in the plane. The learning objectives for this section, you do not need to write down these learning objectives, but take a look and listen. We're going to be representing vectors as directed line segments. We're going to be writing the component form of vectors. We're going to perform basic vector operations and represent them graphically. We're going to write vectors as a linear combination of unit vectors. We're going to find the direction angles of vectors, and we're going to use vectors to model and solve real-life problems. All right, so you understand what's going on here. Force and velocity involve both magnitude and direction. They cannot be characterized by a single real number. You need a directed line segment. A directed line segment has an initial point P and a terminal point Q, and its magnitude, which is its length, is denoted by this symbol, which is read magnitude of vector PQ. So if we put like double bars around the vector, we're talking about the magnitude of the vector, all right, which means its length, okay? And we can find the length, as you know, by using the distance formula. All right, two directed line segments with the same magnitude and the same direction are equivalent. Vectors are represented by lowercase boldface letters. So you can see how I've made these bold. U, V, and W are the most common letters used to name vectors. All right, but they're boldface. All right. All right, so let's take a look at example 1. And did everyone get my 6.3 gift? All right, I'm sure hoping this is your first one right here. Let U, vector U, be represented by the directed line segment from point P, 0, 0 to Q, 3, 1. And let V be represented by the directed line segment from point R, which is at 2, 2, to point S, which is 5, 3. Yes. Okay, so I'm asking you to show that the magnitudes are equal. All right? So we're going to show that the magnitudes are equal. How do we do that? Distance formula. So to find the magnitude, let me get this up here. We're finding the magnitude of PQ, so let's draw PQ. Did I give you a little graph to put this on? So 0, 0 to 3, 1. 0, 0 to 1, 2, 3, 1. So this is PQ, that's vector PQ. And we want vector RS, which goes from 2, 2 to 5, 3. So this is from R to S. So it's a directed line segment, so we have to state that we're heading from P to point Q, and we do that with a little arrow from P to Q. All right, we're trying to show that these two vectors, I didn't draw them, well, I did as best I could, but we're trying to show that they have the same magnitude, so that means that they have the same length. As I'm sliding this one over, I think you can see that that's going to work, but let's actually get the numbers. So using the distance formula, for this, we would want to say distance between, this is 0, 0, and 3, 1. So distance formula, we would want to do 3 minus 0 quantity squared plus 1 minus 0 quantity squared. Everybody agree?
Yes.
So we get square root of 9 plus 1. I get square root of 10. Would you please verify that you're getting the same result for our vector RS? Remember, when we draw the vertical lines around the vector, that means we're talking about the magnitude. So I'm asking you to find the magnitude of vector RS and show that it's the same as the magnitude of vector PQ. Do they match?
Yep.
All right, I'm doing 5 minus, is it 5 minus 2? 5 minus 2 quantity squared plus what? 3 minus 2 quantity squared. So we're getting 3 squared is 9 plus 1 squared is 1. We're still getting square root of 10. Everybody agree? All right, so we've shown that the magnitudes are equal. But remember, what are we actually, overall, what are we trying to show? We're trying to show that these two vectors are equivalent. And that takes two parts. And we just covered part A of the two parts. We showed that they have the same length, but that's not enough to show that the two vectors are equal. You also need to show that they have the same direction. So this is the second part that we need to do. How do you think we show that they have the same direction? Okay, the arrows are pointing in the same direction. They're both heading from, from somewhere to the upper right, right? They're both going up and to the right. But what do we need?
Slope.
Slope. Thank you, Chad. So we want to find the slope. Find the slope. Slope of vector PQ. And we need the slope of vector RS. All right, and so the slope, you're calculating this.
If it's like negative 1 over 3, then it wouldn't be the same, even though it's like the same slope because it's going like the opposite.
Are you getting this? Are you getting the same slope?
Yeah.
1/3 for both?
Yep.
Yes? Positive 1/3? Okay, so our slope for the first one is 1 minus 0 over 3 minus 0, so that's 1/3. And the slope for the next one is what?
3 minus 2 over 5 minus 2.
All right, and again, we're getting 1/3. Are we okay with this? So they have the same slope, and they have the same distance. So that means that the two vectors are equal to each other. All right. All right, so let's talk about the component form of a vector. If a vector has 0, 0 as its initial point, like vector PQ did in our last example, if a vector has 0, 0 as its initial point, we say that the vector is in standard position. So vector PQ was in standard position, vector RS was not in standard position. Everybody understand? You with me from our last example? Okay, we can represent a vector in standard position just by listing its terminal point. So for vector PQ, from our last example, I mean, we said, oh, P is 0, 0 and Q is 3, 1, but we could have just written it in its component form by just writing its terminal point, which was 3, 1. And we used these fancy, I'll call them vector braces, if you will, all right? And it would just be written like that. So vector PQ that we had from our last example could have just been written like this. 3, 1 in vector braces.
Why would you do that? What's the
Oh, what's the benefit of that? The benefit is then I only need to write one pair of numbers to represent a vector instead of, oh, I went from 0, 0 to 3, 1. I can leave off the 0, 0 part and just say, here's my vector because it started at the origin and it went to the order pair 3, 1.
That only works if it's standard position.
Only works if it's in standard position. All right? The RS, we could still write it in component form, but we would have had to slide it over and put it right over PS to do that. Does that make sense? Or was that right, PS? PQ, excuse me.
Would you want to do the hot test or do you
Hold that thought. Hold that thought. All right, the coordinates V1 and V2 are said to be the components of vector V. So in this case, V1 would be 3, V2 would be 1. Those are said to be the components of vector V. All right, if the initial and terminal points lie at the origin, then let me start again. If the initial and the terminal points, let me underline and, if the initial and the terminal points lie at the origin, then vector v is said to be the zero vector, all right? And it's denoted by a bold-faced 0, and in component form it would just be 0, 0, with vector braces, all right? So we're talking about what's a zero vector. A zero vector is a vector whose initial and terminal points lie at the origin.
Which ones are the terminal points?
Pardon me?
Which ones are the terminal points?
If we go back to this example here, for example, R was the initial point and S was the terminal point, all right? And in this case, P was the initial point and Q was the terminal point. All right, so component form of the vector with an initial point P equaling P1 comma P2 and terminal point Q, where Q is Q1 comma Q2, is given by vector PQ is going to be, again, we use these fancy vector braces, and we just subtract our x's from each other. So Q1 minus P1, always taking terminal minus initial, and then Q2 minus P2. All right?
I have no idea what is that.
So my point is, if we were going to put vector RS in component form, if we wanted to put RS in component form, remember it's going from 2, 2 to, 5, 3, was that correct?
Yeah.
We would do that, component form for this, we would just do 5 minus 2, we're not doing anything with midpoints. We're taking the distance between our x's and our distance between our y's. So 5 minus 2, comma, 3 minus 2. And guess what we get?
Wait, so it's Q1.
We get 3, comma, 1. So it's going to have the same component form as PQ. So vector RS has the same component form as vector PQ. Why? Because they really are equal vectors, right? I can put this one, I can put this one directly over that one, right? Same deal? All right, going back here. All right, so all we did was we wrote vector RS from our first example in component form.
Wait, so
You know.
thingy is like that,
Vector braces, I'm calling them.
sure. So, like, the final answer, what does that get you? Like, if you have those two things and then, like, values in between. Like, is that the vector?
That's a way of writing a vector. It's called component form, right? And the first number, your first component, is how far the x changes in your vector. It's like the x change, all right? And the second number in your second component is going to be how far the vertical changes, right? How much the y changes. All right, so in that last example, our vector RS could be written in component form as vector 3, comma 1, right? And that means the change in the x was 3 units and the change in the y was 1 unit. That's all it is. And it doesn't matter where the initial point is and where the terminal point is, because the component form is going to be the same no matter where we start it and where we end it. Does that make sense?
So, like, the component form for, like, that would be, like, the 2 points subtracted from each other, and then, like, for the 0, 0, it would be, like, the final ending.
Correct.
Sorry.
That's right. Okay, so the magnitude or the length of vector v is, magnitude of vector v is going to be square root of q1 minus p1 quantity squared plus q2 minus p2 quantity squared. We already did this with the first example. Or if it's just in component form already, then you just need to square the v1 and square the v2, add them together, take the square root. All right? So if I say, do I have an example coming up? All right, no, I don't. So let me do this. So let's say I give you a vector and it's in component form, and I'll say it's 4, 1. If I ask you to find the magnitude of this vector, I'm going to call it V. Notice I'm using boldface V. All right, if that's my vector, if I want to know the magnitude of vector V, I would just do square root of 4 squared plus 1 squared, and I'm going to get 16 plus 1, I'm going to get square root of 17. So the magnitude of this vector is going to be square root of 17, which means the length of the vector, square root of 17. Cool.
Like problems and stuff for homework, and then like the inevitable test. Should we like try and face this stuff?
Sure. That's good form.
Get points off if we don't.
Let's worry about understanding vectors, all right? Okay,
Wait, what do we bold?
the name of the vector, if it's written with one letter, it's put in boldface, okay? All right. So if, I'm waiting, if the magnitude of vector V is equal to 1, then vector V is said to be a unit vector. So in other words, if your vector's length is exactly 1 unit, it's said to be a unit vector. It's 1 unit long.
How can you get back to type 1 you get like, you know,
So for example, if I say my vector is 1, 0, I'll call this vector W. All right? Then the length of vector W is going to be square root of 1 squared plus 0 squared. Isn't that just equal to 1? Alexis, you with us? So this vector right here would be a unit vector because it has a length of 1. Oh, Maria, you are a day ahead of us. We're going to get to the connections between vectors in the unit circle probably next class. All right. But, yeah, and, all right, so let's take a look. Oh, wait, I missed this one. If the magnitude of, if the magnitude of vector V is equal to 0, then vector V is said to be the 0 vector, and it's denoted by the boldface 0. All right? Boldface 0 is indicating this is a 0 vector. It's actually got that as the symbol. All right. So here is our next example. Is this on your gift?
Let's do it.
All right, so I'm asking you to find the component form, find the component form and the magnitude of vector V that has initial point P at negative 2, 3 and terminal point Q at negative 7, 9. Would you take a minute to work this out, please? Did I give you a place to sketch this? Did I give you a little graph?
what the graph is for.
Yeah,
There's 3 we're drawing. Here's a 2. I think 3 we're drawing on that. I was gonna do.
Oh, yeah, maybe you want to do it up above on the graph for number 1 or something, wherever. I just think, I'm a visual learner, so I kind of want to see the graph, even though I didn't sketch this vector. I still think it's helpful to learn that way by actually seeing a picture of what's going on. So if you want to sketch this somewhere or on your own piece of graph paper or squeeze it onto number 1, that's fine. So here's point P, which is negative 2, 3, and point Q is negative 7, 9. Say that again? Those are your, yes. So these are your x's, right? And these would be your y's here, correct? All right, so talk me through this. How do we put this into component form, vector v is going to be, what am I doing? To find this in
It would
component
be,
form.
-7.
How'd you get -7?
That's the,
Oh, go ahead. So -7, I'm with you.
and then -2.
Minus a -2.
And then, 9 times.
Everybody agree? Difference in our x's, difference in our y's, but keep in mind you have to go from, it's got to be terminal minus initial, right? Terminal minus, right, you got to go terminal minus initial, not initial minus terminal.
Can you not do initial minus terminal at all? If you did it both ways, do that?
You do not want to do initial minus terminal, because then your vector will be going the other direction.
Oh, okay, sorry.
Alright. We're naming it boldface v. It just says find the component form and magnitude of vector v that has initial point p and terminal point q. I mean, sure, we could have called it vector pq like this, but they're saying call it v for this example. All right. So at this point, what did you end up getting? Do people agree with that? -5, 6 in our vector braces. That is the component form. All right, and we're supposed to find the magnitude. So what's the magnitude of vector v going to equal? 61? The square root of 61, because this is what? -5 squared plus 6 squared, agreed? And so we get 25 plus 36, and that is 6 square root of 61. Are we okay with this?
Can we not write it as like the actually one put it down?
What do you want to write it as?
As in like actually solve the square root of 61, so it's south.
We're keeping it exact.
Okay.
Okay. All right, moving on. All right, so let's talk about vector operations, scalar multiplication, and vector addition. Chad.
Where do vectors come into play in real life?
Wow, all over. When you take physics, I believe that you'll be doing vector work with physics. Anything to do with flights, we're going to have some real life examples with force. You know, different forces acting on things, and when different forces act on an object. Like if I'm pushing this way with a certain force, and Cindy's pushing it up like this at the same time, then what's the overall movement of this thing? It's going to be sliding more like this. You with me? Does that make sense? So that's a physics kind of thing, but we could also talk about flights, you know, vectors, and we're going to get some examples like that. Brian. Okay, so when we multiply a vector by a scalar, that's supposed to say that can be thought of, little typo, that can be thought of as changing the length of the vector. If the scalar is negative, we are changing the direction to the opposite of what it was. So I think this is this your next example?
Yes.
All right, so vector 3, 4, go ahead and draw vector 3, 4. If you just see this component form of 3, 4, we can start with the initial point at 0, 0 and go to 3, 4. And there's our vector v. Everybody with me? And then we want to try -2 times the vector v. The -2 here is a scalar, which means it's a constant that we're multiplying something by. You could multiply a matrix by a scalar. You can multiply a vector by a scalar. All right, and so if I multiply -2 to the 3 and the 4, would you agree that we would get -6, -8 in vector braces?
Can't you also divide?
Well, our scalar is -2, so we're multiplying both of these by -2. But I mean, if you want to have a new vector like let's say 1/3 times vector v, right? 1/3 times vector v, we could get, 1, 4/3, if that's what you mean by dividing. All right, but right now we're graphing -2 times the vector. Did you graph this? Pardon me? Sure, I just gave this as a 1/3. So 1/3 could be our scalar. I just wanted to give you this one because I wanted you to notice that if you multiply by a negative, what happens? It changes the direction. Now we're heading the other direction. We're going to -6, 8. -6, -8, which is right here. So that vector looks like this. This is the -2 times vector v. Are we okay with this? It's twice as long, and it's going in the opposite direction, Alexis.
Would you give it to us like that? Would you give it like 2v equals and then have like the double points, or do we need to find like the double points? Would
Are you
say-
asking for finding the magnitude?
No, like if it says now try -2v equals -8.
No, I mean, now try finding -2v, and I already gave you the answer.
Okay, so
Right.
you would usually need to find.
So you would need to multiply your vector yourself by that scalar. All right? Okay, and so, all right, so we good with this? Sure, it could be.
Yeah.
All right.
Yeah.
All right, to add two vectors geometrically, you will position them without changing their magnitude or direction. You position them so the initial point of one vector coincides with the terminal point of the other vector. The sum of two vectors, like sum of vector u plus vector v, is called the parallelogram law. Let's see why. And vector u plus vector v is called the resultant of vector addition. So let's just make up two vectors. Let's say we've got vector u as, let's say, 2, 4. And let's say we've got vector v as, let's say, 5, 1. All right? So if I'm going to graph these, and if I didn't give you any room, maybe you want to grab a piece of, did I give you room to do this?
You gave us a graph.
Oh, but I did, did I give you, 1, 2, and 3, 1? All right, well, let's do those instead. 1, 2, and 3, 1. All right, so if I graph vector u, which is going to 1, 2, that's this little vector right here, that's vector u, and vector v I know is 3, 1, which is this vector, but hold on, don't draw it there though, okay, because really we want to put that so that the initial point of v is at the terminal point of u, so we want to put it like this. Do you see how I put vector v, the initial point of vector v, at the terminal point of vector u? All right, why are we doing this? Because we're adding the two vectors together.
Oh.
So vector u plus vector v is going to, looks like it's going to end up right here at this point. You with me? So the resultant vector is going to be this vector here. That's going to be the resultant vector. Why is it called the parallelogram law? Because your resultant vector is actually the diagonal of a what? Well, it forms a triangle, but it's actually going to be the copy, paste. It's actually going to be the diagonal of a parallelogram. Let's see this little bit. Copy, paste. Right? It's actually the diagonal of a parallelogram where u and v are consecutive sides. All right? Okay, so well, yeah, but we're showing it. We're showing it geometrically. We just added two vectors geometrically, which means we're showing it on a graph, right? And using geometry, because parallelograms tie in with the geometry. All right, so, but we are ending up where?
Wait, so then do we just find the IDK?
U plus v is going to be, add those x coordinates together, add those y coordinates, you with me? Does it end up being 4, 3?
Yes.
Yeah.
And is that what we got graphically?
Yeah.
Yes. Are we okay with this?
No.
Bless you. Questions on
Wait,
this?
what do you mean is that what we got graphically?
Is that where the terminal point? Yeah, all good? Okay. All right, so the definition of vector addition and scalar multiplication, here, these are the formal definitions. If we let vector u be u1 comma u2, and vector v be v1 comma v2, we're letting those be vectors, and we're letting k be a scalar, then the sum of vector u plus v is going to be u1 plus v1 comma u2 plus v2, which is exactly what we did right here. And the scalar multiplication of k times vector u is going to be the vector k times vector u. We could put the k on the outside of the vector, so k times vector u, which is u1 comma u2, or we could bring that scalar inside and multiply it by each of these and say that the vector k times u is equal to k times u1 comma k times u2. Questions on this? Pardon me? Backing it up. You could. But it is a directed line segment. It has an initial point and a terminal point. Directed meaning it's not just a line segment, it's got a direction. All right, and it has a magnitude, which is represented by the length. All right, it's got a certain direction and a magnitude. All right. All right. Where were we? Here? Okay. All right, the negative of vector v, where v is v1 comma v2, is going to be opposite of vector v. Just take the opposite of v1, opposite of v2. The difference of vector u and vector v. Now we're not adding, we're not getting the sum, we're getting the difference. So vector u minus vector v is the same as vector u plus the opposite of vector v, which we could get by taking u1 minus v1 and u2 minus v2. Right here?
Yeah.
Okay, so we did the u plus v so far, right? We did part A. We didn't do parts B or C. Okay, so if we're going to do u minus v on our gift, are we still using, what was u? And what was v? All right, and if we want to do u minus v, negative 2, 1. All right, let's see, that's doing it arithmetically, right? Let's see how we would do this geometrically. All right, if we're doing this geometrically, all right, if we represent u and v with the same initial point, then the difference, u minus v, is the vector from the terminal point of v to the terminal point of u, which is the same as u plus the opposite of v. All right, and I'm just trying to make this nice and big. I'm making this jumbo size. All right, so here's vector u, which is going from, you with me?
Yeah.
All right, and we've got vector v, which is 3, 1. That's this one. Agreed? Right?
Yeah.
Okay. And it says geometrically, if we represent u and v with the same initial point, which is what I've done, then u minus v is going to be the vector from the terminal point of v to the terminal point of u. That's this vector right here. All right. So, all right. So Cole is noticing that this vector is not the same as this vector, or is it? Because if I write this vector, what is this vector? This vector goes from 3, 1, as the initial point to 1, 2 as its terminal point. If I want to put this vector, I'll call it vector W for conversation's sake. If I want to put vector W in component form, remember we only use those vector braces on component form. Wouldn't I do 3 minus 1 and 1 minus 2? Is that correct?
Yeah.
No, I messed up. No, remember it's always terminal minus initial. I messed it up. So I want to do terminal minus initial. So I want to do 1 minus 3, comma 2 minus 1. So is that the same as what we got here?
Yes.
John? Where you write this? What do you mean?
Where we graph it. Do I have to graph it there, or do you graph it at the origin? Because it's the same vector, it doesn't matter.
I think to answer your question, geometrically, you find the vector just like we did, and it's sitting here, right? You could say, oh, how does that relate? And you could say, oh, wait, that's the same as the negative 2, 1 vector here. But geometrically, we find it by drawing U and V with the initial points the same, and then going from the terminal point of V to the terminal point of
So
U.
I have to write it there.
Graphically, I would show it like this,
Okay.
but arithmetically, you're going to get this. And if you put this vector right here into component form, you're still going to get this.
Why did we not just write like 1 minus 3 comma?
Pardon me?
Why can't we just say like 1 minus 3 comma 2 minus 1 and call it a day?
What-
Like, I mean, guys, you have to solve it so you finally get like negative 2 comma. Why do we have to go to like the extra length to graph it? Why can't we just like?
We can find things in more than one way
Yeah.
in math, and that's what we're doing. We're finding the difference in two vectors arithmetically, like we did here, and geometrically, like we did here. You need to be able to do both ways. All right, because I know that's your next question, Alexis. All right. Okay, so we already did this, correct? All right, did we? I'm gonna skip this. Excuse me. You're going to do the 2u minus 3v on your own. All right, you're going to do that geometrically and algebraically. I'm going to let you do that.
In English. Wait, I just
Good.
We know how to graph it.
That's what we just did, right? No.
No.
Which listen, no, that's not nice. Graph it the same way as just the minus.
You're going to still do this type of geometrically. You're going to do 2u and 3v from the same initial point, and then take from the terminal point, right? I'm going to let you do that one. I want to see that you can do that. All right, so take a look at the properties of vector addition and scalar multiplication. I don't think I have these here. Yeah, we are. Yeah, no, do not do that now. I want you looking at page 451 with me, please. Page 451. Everyone has their book open. Page 451. On page 451 at the top of the page, it says vector addition and scalar multiplication share many of the properties of ordinary arithmetic. So these are the properties of vector addition and scalar multiplication. Let u, v, and w be vectors, and let c and d be scalars. Then the following properties are true. Is everyone with me on page 451? Okay, property 1, that vector u plus vector v is going to be the same as vector v plus vector u. Property 2 says vector u plus v added first and then added to vector w is going to be the same as if you take u plus the sum of vectors v plus w added first. So in other words, what have we learned so far? That vector addition is commutative, that's example 1, and vector addition is got the associative property. All right, property 3, if you take the u vector plus the 0 vector, you're going to get back to the u vector. All right, Property 4 says if you take the u vector and add to it the opposite of the u vector, you will get the 0 vector. Makes sense? If you go from, 0, 0 to 3, 1, and then you go from 3, 1 back to 0, 0, don't you end up, when you add those, you end up at 0, 0. All right, property 5 says scalar c times d times u, same as multiplying those scalars together first, and then multiplying by vector u. You with me? All right, and then number 6, if you have a scalar c plus d and you want to multiply that by vector u, that's okay to multiply vector u by c first, and then add it to vector u times d. All right, property 7, scalar c times the sum of vectors u and v is the same as taking vector u and multiplying it by c, and vector v and multiplying it by c, and adding them together. Property 8 says 1 times vector u is equal to vector u. So in other words, if your scalar is 1, you just get back to the same vector. And 0 times vector u is going to give you the 0 vector. All right, so if your scalar is 0, you wipe out your whole vector. All right, and then property 9, if you are trying to find the magnitude of scalar c times vector v, that's the same as taking the absolute value of scalar c times the magnitude of vector v. All right, so that's it for those properties. Let's take a look at unit vector.
Oh my gosh, the vectors from back to 1830s, that is ridiculous. William Rowan Hamilton. Wow.
All right, so it is often helpful to find a unit vector that has the same direction as a given non-zero vector v. To do this, you're going to divide the vector v by its magnitude to find the unit vector, and we'll call it u. So we're going to let lowercase u in this case be the unit vector. So the unit vector, oh boy. So the unit vector u is equal to vector v divided by the magnitude of vector v. Or you could think of it as 1 divided by vector v, 1 divided by the magnitude of vector v times v. Do I have an example? Yeah. This given a, I don't even know what I wrote, unit vector in the direction. U is a scalar. All right, here, let's take a look at this example.
Give it 2 minutes, we'll just call it a day. Call it a day.
Excuse me. Is this example in your gift?
Yes.
All right, so did you start off by finding? Are the announcements on? I want to hear these. Stop talking, please.